lecture series of optical instrumentation. This is lecture number 10, and in this lecture we shall discuss about remaining lasers, and then we will be discussing about detectors, light detectors. Okay. So, next is CO2 laser, carbon dioxide laser. It is a molecular laser, as I have already told you. Now, in molecular lasers, the energy levels are provided by the quantization of the energy of vibration rotation of the constituent gas molecules. Mainly in gas molecules, what happens, there are vibrational modes and rotation modes. The atoms are vibrating and rotating continuously, and when any molecule jumps from one vibrational mode to another vibrational mode, it emits a photon of significant wavelength or frequency, and this is how we get laser. Okay. So, over here you can see the CO2 molecule, and it has three vibrational modes, a bending mode, a symmetric mode and asymmetric mode. The CO2 molecule is basically an inline arrangement of two oxygen atoms and the carbon atom, which can undergo three fundamental modes of vibration: bending mode, symmetric mode and asymmetric mode. Okay. At any time instant, any given time, CO2 molecule can be vibrating in any linear combination of these fundamental modes. Okay. At any given time, any CO2 molecule can be vibrating in any combination of these fundamental modes, but basically there are three modes: symmetric, asymmetric and bending, that are shown in this diagram. You can see this is symmetric mode. Okay. Carbon atom is over here, oxygen atom is vibrating. If this atom is vibrating outward, this atom will also vibrate outwards. So, if this moves inward, then this also moves inward. So, this is symmetric bending. This is bending, sorry, this is symmetric vibrational mode, and this is bending mode. In bending mode, what happens? Oxygen molecules vibrate in these directions, and carbon molecule also atom also vibrates like this, and oxygen atom also vibrates like this. Okay. In this, carbon atom is not vibrating at all. What is asymmetric mode? In asymmetric mode, carbon atom vibrates and oxygen atom vibrates, but how? Like this. Oxygen atom is vibrating and carbon atom is vibrating towards this or this. So, this is asymmetric vibrational mode. So, these are the three fundamental modes. Any molecule will be vibrating in any combination of these three modes. Okay. So, these vibration modes are denoted by quantum numbers. The modes of vibration are denoted by a set of three quantum numbers. V1, V2, V3, which represent the amount of energy associated with each mode. Okay. Like for example, 100, it means that a molecule is in the state is vibrating in a pure symmetric mode. Okay. 100, it means the molecule is vibrating in pure symmetric mode with one quantum of vibrational energy. How much vibrational energy? 1. Okay. If 010, it means it is vibrating in bending mode, pure bending mode with one quantum energy, and if 001, it means it is vibrating in pure asymmetric mode with one quantum energy. Okay. Now, this is the energy band diagram of CO2 laser. Active material 2, CO2. In CO2 laser, active material is a mixture of carbon dioxide, nitrogen and helium. In what ratio? 1:4:5. So, 1 part carbon dioxide, 4 part nitrogen gas and 5 parts of helium. Why nitrogen? Again, like in helium neon laser we have seen helium is used for excitation. Similarly, nitrogen plays important role in excitation of CO2 molecules. So, first nitrogen molecules get excited and they transfer their energy to CO2 molecules through collision. Excited nitrogen molecules transfer energy to CO2 molecules in resonant collisions, exciting them to which level? 011 level, pure asymmetric with 1 quantum energy. Okay. CO2 lasers are highly efficient lasers and that is why they are used in industries. They generate very high power lasers. They have efficiency as high as 30%. Okay. So, over here this is energy level diagram of CO2 laser. Nitrogen, carbon dioxide, energy that is given through pumping, electron collision is given to nitrogen and nitrogen atoms are excited, and through collision they are transferring energy to CO2 and in which asymmetric over here, exciting them to 001. So, that is why this is asymmetric vibrational mode, and when this CO2 molecule from asymmetric vibrational mode it go to symmetric mode and bending mode, and when it jumps from asymmetric mode to symmetric and bending mode we get laser transitions different. Over here you can see this is 10.6 micrometer, this is 9.6 micrometers, and through again collisions and through fast decay they finally come to ground state. Okay. So, this is how CO2 laser works. This is the construction of CO2 laser. Over here the mixture of helium, nitrogen and carbon dioxide inside this through electron discharge, power pumping is done, and this is airtight tube and this is the cavity you can see. So, the photons keep on reflecting from this side to this side and finally they come out over here because this is partially reflected mirror. Okay. Various type of CO2 lasers are available. The power output of CO2 laser is approximately proportional to the tube length. So, we can increase the power output by increasing the tube length. So, there are CO2 lasers of more than 10 meters of tube length are constructed for this purpose. Okay. Also, it is easy to obtain continuous wave laser of around 100 watt output from only 1 meter long tube. Okay. So, we can get very high power output and that is why these lasers are used in industries. So, this was all about CO2 laser. Next and last is liquid dye laser. Okay. So, there are few drawbacks of solid lasers and few drawbacks of liquid lasers. What are they? Solid lasers are very difficult to prepare required requisite degree of optical homogeneity and they may suffer permanent damage if overheated. If active material is in solid form and if it overheats, then the material can be damaged permanently. The crystalline structure of the material is disturbed and so the active material is damaged if it is overheated. Also, it is very difficult to construct a solid material with very high homogeneity, right. So, this is a drawback of solid lasers. In gaseous lasers we do not have this drawback, but the molecules, the atoms of active material is very less in gaseous lasers. Okay. Gases do not suffer from these difficulties, but have much smaller density of active atoms. We need higher density of active atoms, so that we can get more output. Okay. So, liquid material can overcome both these drawbacks. So, the most important type of liquid laser is dye laser. Okay. In liquid, if active material is liquid, the density of active material is atoms is high and also it can be homogeneous, it can be made easily homogeneous, and permanent damage is less likely if it is overheated. Okay. So, we have to discuss liquid dye lasers. It can be tuned over a significant wavelength range, we can tune it for different wavelength range. What is active medium? Active medium is organic dye that is dissolved in a particular solvent. There are various different solvents are available. So, this is the energy band diagram. You can see the dye molecule has two groups of closely spaced electronic energy levels, the singlet states and the triplet states. These are singlet states and these are triplet states. The singlet states occur when the total spin of the excited electrons in each molecule is 0. So, basically it is a 4 level energy level system and threshold can be reached at a very small population inversion. Okay. So, over here pumping actions 4 energy level system 0, 1, 2, 3 atoms are getting excited and through decay, and after that through laser transitions we get lasing action. Okay. This is the construction of liquid dye laser. You can see this is the dye over here, active material, fine, and these are the pumping radiations. For pumping what we are using? Argon laser. Sometimes we use lasers as pumping mechanism for other lasers. Okay. So, over here this radiations are falling on this liquid dye, and through pumping atoms are getting excited, electrons are getting excited, and again after spontaneous emission and stimulated emission we are getting photons, and you can see these are cavity, these are 100% reflective mirrors. So, again by reflecting again and again we are getting amplification, through stimulated emission, and after that what we are getting? We are getting output over here, continuous wave output, and we can tune it over here. There is a tunable element, and output mirror is 95% reflective. So, 95% of the radiation will go back, and only 5% of radiation we get over here, 5%. Okay. So, why do we need this? We need this to achieve stimulated emission. We need photons, sufficient amount of photons to get stimulated emission over here. So, all the dye lasers are optically pumped with the pumping source having a wavelength slightly less than the laser output. Okay. So, wavelength is slightly less, so frequency is slightly more. So, energy of this photon is slightly more. Many dyes have been used as laser media, but rhodium 6G with methanol as a solvent is one of the most successful. Okay. So, this is mainly used, rhodium 6G with methanol as a solvent. The efficiency of this is 20% and the range is 570 to 660 nanometers. So, this was all about lasers. We have discussed solid lasers, gas lasers, liquid lasers, semiconductor lasers, and before that we discussed LEDs. So, we are finished with sources of light. Next we shall move to light detectors, and to measure the efficiency of any light detector, mainly PN diode, PIN diode, we use two terms, that is quantum efficiency and responsivity of that light detector. So, what is quantum efficiency? It is denoted by eta. Quantum efficiency is denoted by eta. It is the ratio of number of electrons collected at the terminal, the ratio of electrons, the ratio of the rate of electrons collected at the detector terminals to the rate of photons incident of on the device. How much electrons are collected at the terminal and how much photons are falling on the detector, on the device. So, ratio of the rate of electrons collected divided by rate of photons falling on the device. Okay. If we denote rate of electrons by Re and rate of photons by Rp, then eta is Re upon Rp. Okay. Next term is responsivity R of a photodetector is defined as the output photocurrent divided by incident optical power. How much current is flowing in the output circuit of the photodetector divided by how much power, optical power is incident on the device. Okay. So, if we denote photocurrent by IP, if IP is the output photocurrent in amperes and P in is the incident optical power in watts, then R is IP divided by input power P in. Okay. Now, the output current IP, we can also write IP in terms of rate of electrons collected, and we have denoted it by Re. Okay. How much, what is the rate of electrons collected at the terminal? We have denoted it as Re, and we can define photocurrent in the terms of Re. How? Over here. This is the rate of electrons collected, number of electrons per unit time, and this is charge of single electron E. So, what is this? Charge collected per unit time, charge per second. What is charge per second? Charge per second is current. Okay. So, photocurrent, the output current IP may be written in terms of rate of electrons collected, that is photocurrent is equal to charge of a single electron into rate of electrons collected. Okay. Now, combining equation 3 with equation 1. So, what we can get? IP is equal to E into eta into Rp. What we have done? We have replaced this Re. We have replaced this Re with eta into Rp from equation 1 over here. What is Re? Re is equal to eta into Rp. So, photocurrent is E into eta into Rp. Now, what is rate of incident photon? Rp, total incident optical power divided by energy of a single photon. What is optical power? Energy incident per unit time, energy incident per second, and if we divide that with energy of single photon, we can get number of photons per unit time. Okay. So, this is energy per unit time, that is power, and this is energy of a single photon h nu. So, this is number of photons per unit time, that is rate of incident photon Rp. So, we can put this value, we can put IP is equal to E eta P in upon h nu, right. So, we can put this value of Rp from equation 5 to equation 4. So, we have replaced this Rp by P in upon h nu. So, what is IP? IP is E eta P in upon h nu. Fine. Now, we have to put this value of IP in the equation of responsivity. What is responsivity? Responsivity is photocurrent divided by incident power. So, this photocurrent, we have derived a expression for this photocurrent, IP is equal to E eta P in upon h nu. We replace this IP by this value. So, E eta P in upon h nu and P in cancel outs over here. upon h nu into P in. So, P in cancel out and we get E eta upon h nu, and nu we can replace by C by lambda. So, this is eta E lambda upon h c. So, responsivity is directly proportional to the quantum efficiency at a particular wavelength. Okay. So, responsivity of particular light detector is proportional to quantum efficiency at a particular wavelength. Okay. So, this was about quantum efficiency and responsivity. These are used to measure the efficiency of any light detector, mainly photodiode, pin diode, avalanche photodiode. So, first photodiode that we shall discuss about, simple p-n junction diode. You may have studied this device in your previous years of B.Tech. So, it is a light sensitive diode that converts light energy to electrical energy. Okay. It can be made up of silicon or germanium, but mainly it is made up of compound semiconductor materials. It is a single p-n junction device that works on the principle of photoelectric effect. It is similar to construction as p-n junction diode, except the junction is exposed to light, so that light can fall on the junction. Over here you can see some examples, and this is the symbol. This is the symbol of photodiode. Like I have shown you the symbol of LED. The light was coming outside. In this, the light is going inside. Okay. So, over here the junction is exposed, so that light can fall on the junction. A lens is used to focus the light upon the junction. It is a special kind of p-n junction diode that is used in reverse bias condition. Okay. So, we shall see the function of this diode. So, this is a p-n junction and it is reverse biased. So, P is connected with negative terminal, N is connected with positive terminal. So, what will happen? This when we reverse bias any p-n junction, we know the width of junction region increases. So, this width of junction region will increase, and the holes will move towards P region and the electrons will move towards N region, and this will further increase the width of this depletion region. As soon as any photon falls on this junction region, it gets absorbed and electron gets excited. When electron gets excited, a electron hole pair is created. As soon as electron hole pair is created, due to external bias, what will happen? The hole will move to this side because this is negative, and electron will move to this side because this is positive, and in the output circuit we get a charge equivalent to 1 electron. Okay. And same is explained using energy band diagram. As you can see, when a photon of energy greater than band gap energy of the semiconductor material is incident near the depletion region or on the depletion region, it excites electron from valence band into conduction band and an electron hole pair is created. This we all know, very easy. Electron hole under reverse bias condition drift rapidly towards N and P sides respectively. Due to this, there is a current flow in the outside circuit which is proportional to the number of incident photons. The more number of photons fall on the junction, the more current will flow in the outside circuit. Okay. So, this is how a simple p-n junction photodiode works. We have to connect it in reverse bias condition. As soon as a photon falls, electron hole pair is created, and they both move in opposite direction. Okay. Electron will go to P side, right. Electron will go to N side and hole will go to P side, and due to this we get charge in the output circuit. Mainly this device is used in solar cells these days. For detecting light, it is not very much used. In solar cells also, this simple configuration is not used. Advanced materials and advanced configurations are there, those are mainly used in solar cells. Okay. So, this is the distribution. This is the distribution, this is the optical power. Over here you can see cavity, a photon is falling and it will move inside, it will be absorbed, but only the electron and hole pairs that are generated in this junction region, due to them we get current in the output circuit. So, over here you can see electric field. So, there are huge losses in simple p-n junction diode. We shall see in next lecture how to overcome these losses. Okay. That is it for today's lecture. Thank you.